Alright guys, this is Ashwin here. In this video we are going to do the project for facial expression dataset. So it is also called as facial emotion recognition. So this is a popular dataset that contains around 7 different emotions with a lot of images. So we have like 7 classes and you can see the number of files in each class. Only in discussed we are having like less number of files. You can use some class balancing using Smart in order to uniform the class distribution, but other files seems to be well balanced. It's around like 4000, so that is fine for us. And we also have a test image or the validation image with the corresponding labels. So we are going to use this data set for this project. I am going to build a multi-class image classification model with CNN. Now that we explored the dataset, let's jump into the code. So this is the notebook I have created. If you just go to the dataset, means you just have to create the new notebook. So the data will be loaded automatically. You can use this path directly in order to consume the data. Now first step, we'll just have some code, and first step will be importing modules. So import modules. Now the session is starting. In the meantime, we will import all the basic modules first. So import pandas as PD, import numpy as np, import OS for managing the files, import matplotlib.pyplot as plot. I'll also import cbond here, cbond. And what other basic modules we have? Yeah, import warnings, and we have to set warnings dot filter warnings, ignore, matplotlib inline. So these are the basic modules we have to import. Like most of the project we are importing like this. And this is import cbond as SNS, import Tensorflow as TF, and from Keras models import sequential. And this is for the model creation. So we are using a deep learning module with neural networks, that's why. And one more thing we have to import is the layers. So from Keras layers import dense con2d. This is for convolutional 2d. Dropout flatten max pooling 2d. So these are the required modules for us. And we also import like one more module from tqdm.notebook, import tqdm. Run this. Now we have imported all the modules, so it didn't throw any error. So we will move on to the next step. So the next step will be loading the data set. So load the data set. Okay, now we have to copy the path. So here in the data, you just expand it. So we have until this train, just copy the file path, and here we will initialize train directory equals, paste this. So this is for train directory, and for test directory similarly we will have it for it. So we have got both train and test, and also had this slash. Okay, now that's done. And we are using neural networks, so we can also enable this GPU. Turn on. It will again initialize the session. And after this, we have to define a function because we have to convert this folders into a complete image path with the corresponding labels. We have to do those. So def load images, or you can say load dataset, and here I will pass the directory because we have two directories, train and test. I will again run this modules. Now image paths equals this, labels equals this. Okay, we are just initializing two lists, image paths and the labels. Now I'm going to iterate this directory. So in this directory, if you go further, you will be having the class labels, and inside that you will be having the image file names. So we are going to go through that directory. Now for label in os dot list there of directory. Now we got the label. So if one label is completed, means we can say label completed, maybe at the end we can say. Now after we got the label, we will again iterate further for the file name. So for file name in os dot list directory, the directory plus the labels. Okay, this is only label. I'm just concatenating both this train directory with the corresponding label. So inside this label, it will again go deeper to get the file name, and after that we will concatenate all these things. Now image path equals os dot path dot join of directory label and file name. Image paths dot append image path and labels dot append label. So these are the two things. This is for input, the whole image path, and this is for output label. And we are appending everything into the list, and finally we will return image paths comma labels. So this is the function for converting the folder structure into a CSV. Run this. Now we have to initialize the data frame. Train equals pd dot data frame. I'll also comment this. Into data frame. Now after creating the data frame, we will have train. Okay, I just train of image comma train of label equals load images of train directory. So this is the directory we are going to pass. So this will just return this image path and label, and we are just directly creating a column for each one of them. And after that we will shuffle the dataset. So train equals train dot sample of fraction equals 1. So this is shuffle the dataset. And again, when you are doing this, you have to reset the index. So we can iterate. So reset index, drop equals true. Finally, we will have the train dataset. Run this. Okay, it's saying it's not defined. Okay, this is load data set. Run this again. Now you can see this is the whole image path for the image, and this is the label, and the entire data set is shuffled. So we will get all the different samples for each label. Now we have to do the same for test. So just paste everything. We don't need to shuffle the test data set. So here test dot head, and here also this will be a test directory. So run this. So everything is loaded for the test data. So we are going to use this for the validation purpose. Now the dataset has been loaded successfully. We will go for exploratory data analysis. Exploratory data analysis. Now here SNS dot count plot of df of, sorry, this is not df, this is train of label. So this is the class distribution. Happy has so many labels, and otherwise all the labels are equally distributed. Only for discussed, the labels are so less. That means the number of samples for our train data is so less. We may have to use some class balancing like smart methods or weighted random undersampler, like that. You have to use some methods in order to uniform that. I have done it in some other project video. Maybe you can refer that, or I will just leave this up to you. Now this is the class distribution. Now after that we will just load a single image. For that, from fill import image equals image dot open train of image of 0. Now plot dot imshow image comma cmap equals gray. Now run this. The image actually in grayscale only, so that's why I have to apply this color map, and you can see this is for surprise. No, yeah, this is for surprise. So this is the sample image, and you can see the width and height. It is around 48 cross 48. So that is the resolution of the image. Anyway, for all the images, that is the resolution. Now that we have displayed for this, and if you want to remove this matplotlib thing, just have a semicolon. So this will remove it, and you can also turn off this axis. So we will do that in a separate function. So here I will create the function. Okay, I think we are not going to display it for multiple classes. I'm gonna display everything. So to display grid of images, plot dot figure fix size equals 25. You can also reduce it if you want. Now files equals train of from the starting index. So for that you have to use ilog. That means based on the index you are just getting those samples alone. So this will be 0 colon 25. So I'm just taking the top 25 samples. Now we are going to display a 5 cross 5 matrix of images. So we can see all the different types of classes there. For index comma file comma label in files dot iter tuples. So this is a function for data frame. I'm just iterating through the data frame that is here. Now plot dot subplot. This will be a 5 cross 5 matrix, and index will be index plus 1, because here index starts from 0, but in subplots we have to start from 1. That's why I'm adding a plus 1 here. So in this index we'll be loading the image. So image equals load image of file. This is the entire file path. Now after that we will convert it into an numpy array. So image equals np dot array of image. Now we can just plot the image. So plot dot im show image. Now plot dot title label plot dot axis equals off. So label means it will just display the corresponding label as the title, and plot dot axis off means it will just ignore this axis. So this will just remove those numbers. Let's run this. Okay, load image is not defined. Okay, I think from Keras dot preprocessing dot image import load image. Run this. Now run this. So you can see this is neutral, this is surprise, this is sad, but the resolution is like so small, like 48 cross 48. Maybe we can reduce this to 20 cross 20. Now the blurriness is not there. So you can see different types of classes: angry, happy, angry, fear. Well, there are various emotions, and this is angry. Okay, this is like a sample of images. If you want to display more images, means you can randomly select out some number of images and try to display it like this. So this is for exploratory data analysis, and after that we have to extract the features of the image. So I will call this as feature extraction. We just have to convert that into a numpy array and load it and reshape it in the proper format. So feature extraction. Now here I will say extract features images. Features equals a list for image in tqdm of image. Sorry, this is images. So this tqdm will give you a loading bar, so we can observe the status of how much it is progressed. If you have more number of data, means you definitely have to use this at least to track the images or the process. Now again we have to load the image. So image equals load image of image grayscale equals true, because this is a grayscale image, and again image equals np dot array. Again this will be image. Now features dot append image. So this will do this for all the images, and it will just add it to the features list, and when the process completes we have to convert the features into a numpy array. So features equals np dot array features, and we also need to reshape the array because we have to feed it into the model. For that we have to reshape it. So features equals features dot reshape of len of features comma 48 comma 48 comma 1 and return features. Okay, why we are reshaping in this shape? So first one representing the number of samples. So this will give you the number of samples in the whole data set, and this is the width and height, that is 48 cross 48, and this is the dimension. So usually if you have RGB image, you will be having like 3 dimensions, but for the grayscale image we have to specify like 1 dimension. If you don't do this, the shape will be like this, the number of features 48 cross 48. It won't have this one. So when we are creating the model, it will accept this image, or else you have to like change the model. And why I'm doing this, even if you are going for some RGB images, you just have to change this into 3 instead of 1. So every the remaining process will be the same. The model creation and the training, everything remains the same. You just have to change this alone. Okay, now this is the extract features function. Now we are going to extract the features for both train and test. So I will call it as train features equals extract features of train of image. Run this. And similarly, we are going to do the same thing for test features, extract features of test of image. So this is somewhat around 28,000. I think test features have around like 7K, I guess. Let's also run this. So this will do the extracting. And after that, we have to normalize the image. Normalize the image. So for that, what I'm gonna do is xtrain equals train features divided by 255, and xtest equals test features divided by 255. So why I'm normalizing is the image pixel values will be in the range of 1 to 255. So we are just converting into in the range of 0 to 1. So the neural network can easily capture the information if it's in the normalized range. So this is done. We have to run this afterwards. Now again we have to do one more pre-processing step, that will be convert label to integer. So initially if you see the data set, it is in terms of string. We have to convert it into integer. I'm gonna use label encoding for that. So from sklearn dot preprocessing import label encoder L equals label encoder le dot fit train of label. So fit means it will just see which are the values we have to assign. Let's say if you are assigning integer 0 to surprise, means it will store those corresponding mapping. So that's why we are just using fit only, because we have to transform both the train and test. Now for transformation, I will call it as ytrain equals le dot transform of train of label, and ytest equals le dot transform of test of label. So these are the two, label encoder. Now what this transform does is it will just convert this labels or string into an integer. for both training and testing. So this is the next step. Still the process is going on. I think it will take some time. Now for the configuration, like config, I'll create the input shape variable. Input shape equals, we have 48, 1, and again if you are using RGB images you can just change this to 3, and output classes, output class equals 7. So we have like a total of 7 different output classes, that's why. And also maybe we can convert this label encoding into like a one hot encoding, because this neural network better performs when we are using a one hot encoding. Maybe we will have a snippet for that. Both the train and test feature extraction has been completed. Normalize the image, do the label encoding. Now for this we have to import one more module. So from tf dot keras dot utils dot import to categorical. Sometimes the Keras module won't work for this categorical. I don't know, in the latest version there has been some bug, that's why I'm using tf here. Okay, I can have it as from Tensorflow. Okay, now it's working. So here I'm going to have the same ytrain equals to categorical of ytrain, comma num classes equals 7. Similarly you have to do the same for ytest. ytest. Now run this also. Okay, now all the things are completed. So if you just display, see we are having like 7 columns, 1 2 3 4 5 6 7. So that represents each class. So this is the representation we are using for output. Now we are going to go for model creation. Okay, this will be a long step, I guess. Model equals sequential. I'll just quickly type everything. Sequential of. Now model dot add con2d of 128, comma kernel size. So we will create only one full layer, and after that we will reuse the same information. 3, 3. Activation equals relu. Input shape equals input shape. So this is the first layer, convolutional layer, and after that we will have max pooling. Sometimes they may add what you call the batch normalization. You can also add it and see whether it is improving the accuracy or not. So pool size will be 2, 2, and finally we will add a dropout layer. We don't want to overfit the data set, that's why I'm just having a dropout layer. Usually we can ignore this dropout layer if you have like image augmentation. If you have implemented that may help, but we are not doing any kind of augmentation here because this is like a small image. So I'm just using as it is. I'll just have the dropout layer with 40%. Now we will have this, remove this, do the same for like we are going to have like full convolutional layer like 4 times. Okay, and we will also adjust the number of filters we are going to use. I'll just gradually increase 128, 256, 512, 512. So these are the convolutional layers, and finally we will just flatten all the things we have done so far. So flatten. Now fully connected layer, fully connected layers, convolutional layers, convolutional layers, and here what I'm gonna do, model dot add dense of 512 comma activation equals relu. Okay, this is one dense, and we also need a dropout layer. Just copy this, paste it here, and again I will have one more dense layer. So we will be having like 2 fully connected layers. We'll just decrease this 256, and last dropout we can minimize this, and we'll be having one more dense, that is the output layer. So model dot add of dense of output class comma activation equals softmax. Output class activation equals softmax. So why we are using softmax means if you are having multi-classification means you have to use this softmax. So that represents like a categorical activation function. Apart from that, we have to compile the model. So model dot compile of set the optimizer equals Adam is like a baseline. You can also customize with the SGD. Loss will be categorical cross entropy, and metrics equals accuracy. Okay, everything is good to go. Run this. Okay, it's using Tesla P100 16 GB. That's a good graphic card. If you run it again, it will just remove all those unnecessary things. Now here we will train the model. So I will have history equals model.fit of x equals xtrain, y equals ytrain, batch size equals 128, epochs equals 100, and validation data equals xtest comma ytest. Now let's run this. Let's see. Yes, it is running. We are getting around like 24% accuracy now. It will keep on increasing. That's why we are having like 100 epochs. Let's see how much it is going for 100 epochs. So in the next few lines, I'll be adding a few more things. So here I will plot the train val accuracy with loss. So accuracy equals history of accuracy. Now val accuracy equals history of val accuracy epochs equals range of len of accuracy. So based on the number of samples here in the accuracy list, I will just convert that as an epochs. So this function we usually create for a majority of the deep learning projects. Now plot epochs accuracy blue and label equals training accuracy. That's done. Now similarly we have to do for validation accuracy. Here I will have val accuracy red and validation accuracy plot dot title of accuracy graph plot dot legend plot dot figure. So this will display the labels at the legend, and I think we don't need this. Let's comment it out. Let's see whether it's having any issues. Similarly, we have to do the same thing for loss. So I'm gonna copy the whole thing here so we can easily edit it. Loss. So this will be loss. Everything will be changed to loss. Training loss. Validation loss. Loss. This will be loss graph. Okay, that's pretty much it. Finally, we will just plot the graph. Plot.show. Okay, I think that's pretty much done from our side. We have to plot this graph after the training completes. Currently, we are getting around 58% training accuracy. The epochs around 34, and the validation accuracy is around 60. So we will try to increase more than 60. I think 60 is fine for multi-classification because we are having 7 different classes. So usually you can expect this much accuracy only from multi-classification problems. If you've gone above more than 60, that is a better metric for us. So let's see, we already reached 60, so that is fine for us. Let us wait whether it goes higher or not. In the meantime, we have to test our prediction results, right? So test with image data. This will be plot the results. Now testing with the image data, I will have some image number. So image index equals, I didn't import a random function. Maybe I could have imported that. So here I will import random. Import random. Run this once. Okay. This will run it at the end. I need to get some random image data. So random dot randint 0 comma len of test. So this will choose any index from 0 to the length of the text. Test. Now the image is here. We will display the original output. So print, I'll call it as original output colon y test of image index So this will give us the label. I think this won't give us the label. We have to use the normal test data frame with the label column, test of label of image index. So this will give us the original label. And for the prediction, we have to use like prediction equals model dot predict of x test of image index dot reshape. Again, we already told you why we are reshaping. So we have to reshape like one sample 48 1. So now the reshaping is completed. So this will give us the proper format for the model to predict. After the prediction, I will have another variable called prediction label equals le dot inverse transform of prediction dot argmax. So argmax is whichever probability has higher, like whichever class has the higher probability, it will give you that index. Using that index, I am just converting into a normal label, that is like a string format. Finally, we will print predicted output. Now here I will use this prediction label. Now the final thing, plot dot im show off. Again we have to use the same thing, but here the reshaping will be different. You don't need this one and this one, comma cmap equals gray. Now this is the whole function. Let's see. Okay, now we have got around like 63% validation accuracy. Let's also check whether we have reached like 64. Let's go for 64. Well, it is still loading. Maybe you can also increase the number of epochs because we have used so many dropout layers. So it will take longer time to converge at the global minima. So try to increase the number of epochs like 200 or 200 is sufficient. For this tutorial, I'm just going with 100 itself. I hope it will reach that 64% accuracy because it's almost saturated at 63, I guess. And the train accuracy is keep on increasing. So we have to wait and see. And that's pretty much it. Maybe we can test with some image data and see how it works. Okay, now the training has been completed. Here you can see it gone up to like 64. So as I said, so if we just increase a few more times, means it may reach up to like 67 or even 70 if you just increase the number of epochs. Or you can also play with the model here. So that is also possible. Now that's done. I think everything's ran. Let's run this. Okay, I think we have to use this figure in order to display that also. Yeah, now it's working. So this is the training accuracy. We can see this good fitting here, but after like 40 epochs, the train accuracy is like keep on increasing up to 70, and the validation accuracy is stagnant around like 63. Even in the loss, we are seeing the same thing. We have to even go further. Maybe we can increase the number of layers or the number of hidden units in the model. So these things you can do, but this is the accuracy and loss we are getting. Now let's jump into the testing with the image data. I hope the syntaxes work. Okay, showing some error. Why should be a 1D array got an array of shape in an empty array instead? Prediction label. pred.argmax. Okay, here you just have to add the index because it will return as a list. That's why it's showing another error. Now let's run this again. Why? str object has no attribute prediction label. Okay, this is comma. Okay, now it's showing the original output and the predicted output, both are same. And here you can see the image. And if you want to remove this matplotlib access means, you can just have a semicolon. So this is a wrong prediction. If you run this again, now you can see this is happy. That is a correct one. Again, let's run this. This is also happy. I just want a different class. So this is neutral, but it's predicted as happy. But even I am seeing this woman is like happy only. I don't know. So this is sad and sad. Let's do one more time for some misprediction. Okay, here the original output is fear, but the predicted output is surprise. So yeah, that's pretty much it. But most of the cases we are predicting it correctly. You can also see it like multiple times how it's working, like how the model is performing for random images. You can also use your image obviously for real-time purpose. You can just try to predict your emotion in real time based on your face and do all these feature extraction steps and predict the emotion what you are expressing in the video. Maybe I'll just cover that in later. But that's pretty much it, guys. We have completed the end-to-end project for facial emotion recognition, and this is a multi-classification problem, and we have solved using deep learning. That means with the help of neural networks. And yeah, that's it, guys. If you like this video, hit the like button and don't forget to subscribe the channel for more videos. See you guys in the next video.